Bell's paradox, a visual resolution. Bell's paradox involves two rockets, A and B, initially at rest, and separated by a distance L0. They are attached together by a fragile string of length L0. Let the rockets accelerate with identical accelerations until they achieve a certain velocity v. In the rocket frame, the separation is still L0 because the accelerations were identical, so the string will not break. But in the rest frame, the string will break because it is Lorentz contracted according to the formula L0 root 1 minus v squared, so it can no longer traverse the distance L0. How can the string break in the rest frame but remain intact in the rocket frame? That is Bell's paradox. The secret to the resolution of Bell's paradox lies in challenging the assumption that maintaining a constant distance between the two rockets in the rocket frame corresponds to identical accelerations of the two rockets in the rest frame. To truly see how to maintain a constant distance between the two rockets in the rocket frame, let's employ a space-time diagram whose axes correspond to time in the rocket frame and distance in the rocket frame. We will model the rocket accelerations in the rocket frame as a transition from a constant speed of 0 to a constant infinitesimal speed of delta v. When rocket A changes its speed, rocket B must change its speed simultaneously in order to remain at rest relative to rocket A and not break the string. Recall from this video that lines of simultaneity have slope equal to the velocity delta v, which can be found by reflecting the rocket path about the 45-degree line. So it can be seen from the diagram that rocket B must change its speed later than rocket A. So if rocket A changes its velocity to delta v in time delta t, how long does it take rocket B to change its velocity to delta v? We can use the slope of the green line delta v to discover that delta tb is equal to delta t plus L0 delta v. Now rocket A's rest frame acceleration is delta v over delta t, which we will call A0. Rocket B's rest frame acceleration is delta v over delta tb. Substituting in our expression for tb and dividing numerator and denominator by delta t, we see that rocket B's rest frame acceleration is A0 over 1 plus L0 A0. Another bonus we find out is it's clear from our time equation that delta tb over delta t equals 1 plus L0 A0. So rocket B ages faster than rocket A by this ratio. We found out these same results in this video using Rindler coordinates, but it is nice to be able to arrive at them with just the simple space-time diagram on the right. So, according to an inertial observer witnessing the two rockets, rocket A with the larger rest frame acceleration will continuously gain speed relative to rocket B with the smaller rest frame acceleration. So the distance between the two rockets will become shorter and shorter over time as their speeds increase. This is nothing but the Lorentz contraction. However, since rocket A is catching up to rocket B, their speeds are different, so the Lorentz contraction formula must be modified. For the case of constant rest frame acceleration A0, we discovered the correct modified Lorentz contraction formula in this video. But imagine that instead of giving rocket A a larger rest frame acceleration than rocket B in order to preserve their distance L0 in the rocket frame, the rockets are equally accelerated relative to an inertial observer. Then in the rocket frame, rocket A will not have the necessarily larger rest frame acceleration to keep up with rocket B, so rocket B will pull away from it, and the string will break. For the inertial observer witnessing the identically accelerated rockets, the distance between the two rockets will not contract. However, the string length will contract according to the Lorentz contraction, so the string will break. To sum up, the string breaks in both reference frames if the rockets are accelerated equally, but the string remains taut and does not break in either reference frame if the ratio of the rest frame accelerations is precisely 1 plus L0 A0. Therefore, there is no contradiction, so Bell's paradox is resolved. Thank you for watching.